Space is vast and full of wonders, but nothing bends our imagination quite like a black hole. It warps space, slows time, and swallows light itself. Today, let's step to the edge of the cosmic abyss and peek in. Black holes aren't just a sci-fi prop. They're real predictions from Einstein's general relativity, now confirmed by decades of observation. In 2015, ripples in space-time from colliding black holes were heard for the first time as gravitational waves. In 2019, astronomers revealed the first image of a black hole silhouette. A few years later, we saw the shadow of the monster at the center of our own Milky Way. Each leap pushed these objects from theory into the realm of direct evidence. As we zoom in, the universe gets stranger. Gravity reshapes geometry. Time itself stretches. Energy erupts from near light-speed disks and pencil-thin jets, while the heart of a black hole remains hidden behind a one-way boundary. That paradox darkness powering dazzling light sits at the center of today's story. Imagine packing so much mass into so little space that gravity becomes unstoppable. Space-time curves so extremely that there's a boundary, the event horizon, beyond which nothing returns. Not light, not information, not you. Unlike a star or a planet, a black hole doesn't have a solid surface. The event horizon is not a wall you can touch. It's a point of no return. Cross it, and every possible path you can take leads inward. The escape velocity there is faster than light. And in our universe, nothing outruns light. Physicists describe a characteristic size called the Schwarzschild radius. Roughly speaking, it scales with mass. Squeeze the sun to a sphere a few kilometers wide, and you'd get a stellar mass black hole. Compress Earth down to about 2 centimeters, and you get a planetary black hole. In reality, nature forms them through more dramatic routes. First, stellar mass black holes. A few dozen times the sun's mass. They're the remnants of massive stars that run out of fuel, collapse, and explode as supernovae. What's left behind is a core so dense that not even light escapes. Second, intermediate mass black holes. Hundreds to hundreds of thousands of solar masses. These are the missing link, harder to spot than the small ones, not as flamboyant as the giants. Evidence is mounting from a mix of clues: unusually heavy merger signals, dense star clusters with suspicious dynamics, and X-ray sources too bright for ordinary stars. Third, supermassive black holes, millions to billions of solar masses anchoring the centers of galaxies. Our Milky Way's central black hole is tranquil now, but others blaze as active galactic nuclei, powering quasars so bright they outshine their entire host galaxies. And then there's a bold idea: primordial black holes. Instead of forming from dying stars, they would have been born from extreme density ripples moments after the Big Bang. If they exist, they could range from tiny to titanic, and in some scenarios might even contribute to the mystery we call dark matter. For now, they're hypothetical, but scientists are hunting. Black holes are the ultimate paradox. The darkest objects can power the brightest beacons. Outside the horizon, matter falls inward and forms a whirling accretion disk. Friction and magnetic fields heat the gas to incredible temperatures, making it glow in X-rays and ultraviolet light. Some systems launch narrow relativistic jets, twin beams of particles blasting out at near light speed. These jets can stretch for thousands of light years, punching through mind and sculpting their surroundings. Quasars, blazars, and radio galaxies are all powered by this engine. Gravity turning gravitational energy into radiant power just outside the point of no return. Get close to a black hole and your relationship with time changes. To a distant observer, your clock appears to slow down. Signals you send get redder and weaker. In extreme cases, you would seem to freeze near the horizon, fading from view. From your perspective, though, you could cross the horizon without noticing anything special at that exact instant. Especially for a supermassive black hole whose tidal forces at the boundary can be gentle. Smaller black holes are less forgiving. Gravity's gradient can stretch you head to toe in a process nicknamed spaghettification. Of course, no one is sending probes to cross an event horizon anytime soon. But the thought experiment helps. Black holes are not just heavy, they rewrite the map of what paths through space and time are even possible. Quantum physics adds a provocative twist. In the 1980s, Stephen Hawking argued that black holes should faintly radiate due to quantum effects near the horizon. Over fantastically long timescales, they can evaporate. For stellar and supermassive black holes, this lifetime dwarfs the current age of the universe. This leads to a deep riddle, the information paradox. If a black hole evaporates, what happens to the details of what fell in? Quantum theory says information can't be destroyed, but the classical picture of a black hole seems to swallow it. Reconciling these views has inspired ideas from holography and quantum gravity to speculative concepts like soft hair and firewalls. The jury is still out, not on whether black holes exist, but on what they teach us about the ultimate laws of nature. Black holes don't just feed, they collide. Two black holes can orbit each other for eons, radiating energy as gravitational waves, slowly spiraling together. In the final seconds, their frequency rises, a cosmic chirp, and they merge into a single, heavier black hole that rings down like a struck bell. Gravitational wave observatories transform that idea into data. Each detection encodes the masses, spins, distance, and sometimes a hint of the environment of the pair. By collecting many such events, astronomers are building a census of black holes across the universe, even of those that would otherwise be invisible. In galactic centers, we expect a slower, deeper drumbeat. Supermassive black holes forming binaries after their host galaxies merge. Their waves are so low-pitched that we'll need space-based detectors and pulsar timing arrays to hear them cleanly. Listening at multiple pitches lets us map black holes from stellar scales up to the giants. Supermassive black holes don't merely sit at the center. They can steer the evolution of entire galaxies. When actively feeding, their radiation and jets can heat or sweep out a throttling star formation, negative feedback that keeps galaxies from growing unchecked. In other cases, outflows can compress gas clouds and spark new stellar nurseries, positive feedback that triggers starbursts. This push and pull helps explain why some galaxies are blue and busy, while others turn red and quiet. The balance between feeding the black hole and feeding the galaxy may be one of the keys to cosmic ecology. Over cosmic time, a loose correlation emerges between a galaxy's central black hole mass and properties of the galaxy's bulge. Causation is complex, but the message is clear. Black holes and galaxies grow up together. We can't look at a black hole, but we can watch what it does. X-ray telescopes catch hot disks flickering as matter spirals in. Radio arrays trace jets and even outline the silhouette, the shadow cast against glowing plasma near the horizon. Infrared observations follow individual stars whipping around the dark mass at the Milky Way center, proving a huge invisible object is truly there. And now multi-messenger astronomy links it all. Light, particles, and gravitational waves together. A flare in X-rays might coincide with the change in radio jets. A gravitational wave chirp might be followed by a faint glow if there's gas around. Each channel adds context. Together they turn black holes from mysteries into measurable laboratories. The future of black hole science is bright, ironically so. Next-generation radio arrays aim to sharpen images of event horizon silhouettes and watch them change in real time. Space-based gravitational wave detectors will listen for the deep rumbles of supermassive mergers. Giant optical and infrared telescopes will weigh more black holes by tracking stars near galactic centers. Surveys should uncover more intermediate mass candidates and map how often black holes of different sizes collide. Better theory and simulations, guided by data, will probe how magnetic fields launch jets, how disks break and reform, and how black holes spin up or slow down over a lifetime. Each result tests our understanding of gravity, plasma, and quantum physics in the most extreme conditions the universe provides. The darkest wells in the universe have become beacons for discovery. They bend light, stretch time, and challenge our best ideas. And yet, by studying them, we get closer to the rules that build reality itself. If you enjoyed this journey to the edge of the abyss, stick around. There's always more to explore.